So the next type of electron configuration that we're going to be working on is called orbital notation. And you should write down this blue stuff here where it says orbital notation. The way this is different and special is that we're actually going to draw out our electrons in their orbitals. But we're not going to try and draw out those funny shapes that the orbitals are. We're going to draw our electrons as arrows and our orbitals as simple lines. So we're going to be putting lots of lines, arrows on lines. Now, what you see below with all of these lines is the longest possible orbital notation. And that's not there for you to fill in, and I'm never going to ask you to draw one that is quite this big, but I want you to be able to see this pattern. All of these different orbitals have a different number of lines, or rather, each different letter, each different shape orbital has a characteristic number of lines. If you look through here, no matter whether it is a 1s, 2s, 3s, or even all the way down here in the 7s's, all of our s orbitals have one line with them. Everywhere that we see our p orbitals, once again, it doesn't matter the energy level, no matter whether it's a 2p or a 7p, they always have 3 lines. D orbitals all have 5 lines, and the few f's that we've got have 7 lines. Now this corresponds to the different orientations of each type of orbital on each energy level. If you remember back on page 7, I showed you how we had 3 different orientations of these peanut-shaped orbitals. On each energy level, we have one along the x-axis, the y-axis, and the z-axis, and they all kind of combine and overlap into that electron cloud around the atom. But there are 3 different p orbitals there, and we're just representing each of them as their own simple line. Now, you are eventually going to have to draw your own lines, which is why you have to write down this part here. The first 2 examples, I've drawn the lines and labeled them for you. We're just going to practice drawing the arrows in, but then we're going to practice putting the lines down, and our electron configuration is a guide. So if you haven't watched your page 8 notes yet, that is essential to being able to understand what we're doing here, because we're using those configurations as a guide to tell us what to do with these orbital notations. Now, technically back at the bottom of page 8, there are some rules for how to add our arrows to lines. And these are some pretty simple rules. There's nothing that I really think that you need to add to these rules. I just want to point them out to you so you can just look at them on my screen instead of flipping back. The first rule is Hund's rule. You want to maximize unpaired electrons, which is just a fancy way of saying the electrons don't want to be together if there's open spaces. Just like you wouldn't want to share a bed or like a seat with your sibling at home if there was an open seat or an open bed available. So in this example, if I had some configuration that had D4 in it, our d orbitals get 5 lines. If I only have 4 electrons to put on those lines, then they can each have their own line. There's no need to double them up and have them share lines when there are open lines available. Now, there are going to be times when we do have to double them up, when there won't be enough lines for every arrow to have their own. And when we do that, we need to make sure that they have the opposite spin, which basically means for our arrows, they need to go opposite directions. We can't have 2 arrows going the same direction on the same line. So, let's go fill in some arrows. Like I said, we're going to use our electron configuration as a guide. So I'm going to write oxygen's electron configuration here in order to help us see what we need to do. And because all we really care about is filling in our arrows here, the arrows represent electrons. Remember that these exponents represent the number of electrons in each of these orbitals. So that tells us how many arrows to put on these lines. When that says 1s2, that means we need to put 2 arrows on our 1s line. And if they're sharing the line, they need to go opposite directions. Now, you'll notice I kind of do some weird looking arrows. They're kind of half arrows, because if I start doing double-sided arrows, these start to run together. You might be able to tell I'm already messy enough. I don't need to make anything any messier. These have to have direction. They can't just be lines. They have to have some direction to them. So you need some of those arrowheads there. If you can write these small enough and neat enough, make them fit, but that takes up too much time, and I am not that neat. So it is up to you how you want to draw your arrows. It doesn't really matter. As long as they have a line and a head on them to give them a direction, I'm fine with that. So 1s2 got 2 lines. This 2s2 term means the 2s line gets 2 arrows. And then the 2p lines are going to get 4 arrows. And that would mean 1 on each line before we double up. You might already be able to realize, oh, 4 arrows, 3 lines, 2 of them are going to have to share. I won't be looking over your shoulder during the test to see what order you write them in. So if you want to start with them doubled up and then single, that's fine. But it's an easy habit to get into. If you start with them doubled up, you might write your 2p4 like this, and that is incorrect. These last 2 electrons do not want to share a space if there is an open space available. So it is important that we end up looking like this. And we do generally fill from left to right. So that doubled up set of arrows should be at the far left. It shouldn't be at the far right or in the middle. So as you saw me do at the first kind of step, I always draw mine in left to right, singly first, and then I double up. It's just a good habit to get into, so I never accidentally double up where I shouldn't or have them going in the wrong order. Now, chromium is a bit longer, so let me write out that configuration. But once we have this configuration, we can use that as a guide to fill in what we need to here. Just like before, 1s2 means we put 2 arrows on this line. 2s2, 2 arrows on our 2s line. 2p6 means all 3 of these are going to be full with our doubled up arrows there. 3s2, this is going to be full and doubled up. 3p6, this is full with doubled up arrows. 6 arrows for our 3 lines. Again, trying to make sure I have clear direction on my arrows. 4s2, and then finally 3d4. Just need to make sure that I have my 4 arrows going in those 4 separate spots. Don't let this empty orbital throw you off. We still need that 5th line there. If we were drawing this out, we'd still need to draw it. It's just empty. That empty orbital tells a chemist something about the reactivity of this element. It's either going to be real aggressive about getting 1 electron or about giving up some of these electrons that, don't have it completely full or even completely empty. So there's some reactivity stuff that we know when we see a configuration like this. We have to leave those empty spaces in order to be able to see that and understand that. So let's do some examples where you have to draw the lines. Sulfur's configuration is 1s2, 2s2, 2p4. I take that back. It's 1s2, 2s2, 2p6, 3s2, 3p4. My bad. And so if we use this as a guide, when we see 1s2, we need to draw our lines, and s's only get 1 line. You've got to remember to label it as 1s, and then that exponent 2 means we put 2 arrows on it. Going to the next term, 2s2. S's still get 1 line. They always do. We just label it as 2s, and then we put 2 arrows on it. 2p6. P's get 3 lines. All of them share that 2p label, and then we're filling them all with doubled up electrons because we need 6 electrons on those 3 lines. Then 3s2, s's get 1 line. That gets 2 arrows because of the exponent. And then 3p4. 3p means 3 lines. 4 arrows means just like oxygen, we're going to have doubled up arrows on that first blank and then up arrows on the next 2. And just like oxygen, sorry about that, because these have some very similar ending arrows here, some very similar configurations there on the outermost layer, they're going to have some very similar reactivities. Now for these last 2 elements, I did not do them in class, and I am not going to draw their orbital notation for you here, but I am going to make sure that you have what you need in order to write out that configuration on your own. So I'm going to give you the normal full configuration for them. And then I just need you to turn this into their orbital notation. It's 2, 2p6, 3s, 2, 3p5. So use this as a guide, draw all your lines, make sure to label them, and put all of the arrows where they belong. And then, once you're done with those, you can start looking at pages 11 and 12. Part B on pages 11 and 12 is this orbital notation stuff. Hopefully you already have the complete configuration there, so you can use that as a guide as you're creating your orbital notation. And there are just a couple of problems on page 13 that are orbital notation. So in the top, you're using that to identify an element, and then in question 10, you're identifying if that's correct or incorrect there.